Well, first of all, thank you very much for having me today. It's a real honor to speak in my own country, in Spain. So today I'm going to talk about different things. So I hope you bear with me and you find this as interesting as I find it myself. So we're going to talk about two things. We're going to talk first about the journey of the inverse approximation, and then I'll mention something about the SkyPy project. Okay. But first, let me introduce a little bit myself. So I come from a very theoretical background. I've worked on different things. I've worked on quantum cosmology, effective field theory of dark energy, and I did my PhD at the University of Sussex, working on effective field theory of large-scale structure, redshift space distortions, halo bias. And then after 1 year teaching, I am now a postdoc at the University of Manchester, working with Sarah Bridle in more observational cosmology. I am a member of DES, and I am also one of the co-founders of this fantastic project, SkyPy, that you will learn about today. And of course, I'm also applying for jobs right now. Okay, so enough about myself. Let's begin with the first part of my talk. Here, I'm gonna talk about the journey of the inverse approximation. And this is a series of 2 papers. One is already on arXiv, and 2 available Python packages. Okay, so in this talk, I'm going to walk you through different aspects. So first, I'm going to give you a very brief introduction about cosmic lensing, and then I'll tell you the journey, and then I'll talk about the specifics about the all-angular approach and also the unequal-time correlators, and then I'll show you some results and a summary. Okay, let's start with the introduction. So the first thing I want you to do is to imagine that you're looking at the sky, and that you know that when you see different objects in the sky, every object has its own cosmological distance or redshift. So you have this idea of an onion-like kind of universe. And in cosmology, usually to explore this universe, this onion-like kind of universe, we usually compute correlation between different fields. And just a bit of notation, if you compute correlations between fields at the same time slice, then you talk about equal time correlators. And if you compute correlations between different time slices, then you'll be mentioning unequal time correlators. And in cosmic lensing, there are different examples of fields that are involved. For example, the matter density or the convergence or cosmic shear. And basically, there is this idea that because we are measuring things within our past light cone, we need to project all the fields, and you can compute the angular correlation functions, W of theta, where theta is just the angular separation in this 2D patch of the sky. And well, this W theta, it entails 2 integrals over the line of sight, the radial distance, and then you have different filters that depends on the particular observable that you want to measure, and also in the selection function of your survey. And then we have this factor here, which is the unequal time correlation function, which is nothing but the correlation between matter density fields at different time slices. Then you can do other things. You can expand in terms of spherical harmonics and go and compute the angular power spectrum, the CLs. And this gives you an extra integral over the K range. We still have the filters here, but it appears these spherical Bessel functions and then the unequal time power spectrum, which is nothing but a Fourier transform of the unequal time correlation function. So you are all set, and the next thing to do is just to integrate these 2 things. But a bit of warning here, these are really hard to compute. And the angular power spectrum is even harder to compute because of the highly oscillatory behavior of the spherical Bessel functions. And also because usually the unequal time matter power spectrum is not being very well understood. Right. So how do we compute these integrals, right? And now is where I'm going to tell you the journey of the inverse approximation. To compute these integrals, you can do a few things. For example, you can play around with the filters, you can play around with the Bessel functions, or perhaps you can make different approximations to the unequal time correlators. And historically, the first one trying to solve this integral in concrete, the angular correlation function was Limber in 1953. But for this, he assumed different things on the filters and the correlations. So basically, he assumed that the filters were smooth enough and also that the correlation falls off fast enough that instead of looking at this unequal time information, to just take the mean redshift, and you can compute everything at the mean value. And typically, when you use the Limber's approximation, you also use a small angle separation assumption. And of course, you end up with a much simpler expression of this angular correlation function, but of course, this is not exact. Then 20 years later, Peebles, he applied this Limber's approximation to the case of a sphere and also the discrete case for a discrete survey. But it's not until the late 90s where Kaiser, he also re-derived the Limber's approximation in a different way. He applied this to the flat sky approximation for a curved universe. And in the way, when computing these things, he also used some delta functions. So this looks much familiar to what we are used to in cosmology. And then in 2007, Patrick Simon, he published this very nice paper where basically he focused on addressing the issue of the accuracy of the Limber's approximation. And he concluded that Limber's is a very good approximation only on small angle separations. And if you want to go to larger angle separations, you're better off using something else. For example, he proposes his thin layer approximation. And then the most interesting part is where he compares the Limber's approximation versus the exact calculation. But to do so, he applies also the small angle separation approximation to the exact calculation. So it's not actually the exact calculation. But bottom line from Simon, Limber's is not accurate on large angle separations. Then I told you that you can do something else. You can also play around with the spherical Bessel functions. And typically people approximate these functions to the amplitude of the first peak. And you can do that by using some Dirac deltas. And this is what I call the Dirac delta version of the Limber's approximation. This is very good only on large values of L. So people have tried to put efforts in expanding this approximation. For example, there is work by Leverde et al., and this is what we call the post-Limber's approximation. But there is still this issue regarding the divergence on small L's. Right, and then we're now 4 years ago now, Lemons et al., they published a very nice paper where not only they use the Dirac delta approximation for the spherical Bessel functions, but they also assume different things on the unequal time matter power spectrum. They use the geometric approximation, which basically, instead of having the full information about the correlations between one redshift to another, basically what they do is just compute the power spectrum at one redshift and compute the power spectrum at the end of the shell, and then just multiply both power spectrum and square root it. This geometric approximation is only very good on large scales. And then when you do that, you also end up with a much simpler form. But again, this is only valid for large values of L and small values of K. So what else can we do? 2 years ago, Fang et al., they published another fantastic paper where not only focus on the approximation that you can make with the different factors that they appear here, but also they focus their attention in the K integrals, in the scales of the universe, right? So they split the integrals into two parts, the linear contribution and the non-linear contribution. And for the linear contribution, they are able to compute these things exactly by shuffling the order of the integrals. But then for the non-linear contribution, they claim that they don't need to compute the unequal time matter power spectrum because they also apply the Dirac delta approximation and also the geometric approximation. But this is the point where I'm not very clear about, because the geometric approximation, as I mentioned earlier, is good for large, only for large scales, and nonlinear physics obviously comes into place for increasingly smaller scales, right? So after reviewing all this literature, I came up with this list of still open issues regarding these integrals. So first is the inverse accuracy, the divergence on large angles, and the goodness of the geometric approximation, and how to deal well with the nonlinear physics. And it was very clear to me that if we want to compute these things right, and we want to have and to match the demanding accuracy by the galaxy surveys, we want that in theory, we actually need to compute the unequal-time correlators and also the all-angular calculations of these projections. And this is basically my work here. And now I'm gonna focus on the all-angular approach, and this is a paper that is in preparation, but is already available as a Python package called Corfu. Right, so to explain this thing, let me tell you the story about how I came up with this project. Basically, I was looking at these integrals, and the thing is, I knew how to compute the matter power spectrum for the unequal time context, and I knew how to include nonlinear physics by going to higher order in perturbation theory, using one loop theory, and also effective field theory. And I wanted to see what's the impact on weak lensing observables, but I didn't know how to compute these integrals exactly. So the first thing that came up in my mind, well, I came up with a new approximation that I call the midpoint approximation, where instead of having the full information from one redshift to another, just take the mean redshift. And I wanted to compare with the geometric approximation. But I was really stubborn. I really wanted to compute these things exactly. So in collaboration with one of my colleagues, we started working on a new method, a numerical method, Corfu, that for the first time can give you the exact calculation at all angular scales of this angular power spectrum. And as I say, this is a Python package called Corfu. And for this, what we did is we used FFT-log methods. But the trick here was we avoided the computation of the highly oscillatory spherical Bessel functions, because we took the unequal time matter power spectrum, we inverse Fourier transform it to get the spatial correlation function, and then we computed the angular correlation function here. This wasn't very straightforward because there are some sampling issues that you have to take into account. But then once you have the W theta, you just use the relationship between W theta and the angular power spectrum, the CLs, and just simply perform an expansion in terms of Legendre polynomials and fit for the CLs, and you obtain the exact calculation of the angular power spectrum. So this is basically what Corfu does, and you can already use it. Right, so once we had this, the idea was to analyze all the regimes of validity of all these approximations that I just mentioned, and perhaps at the end of the talk, I can convince you that we can drop any approximation. Okay, and all the analysis for the unequal time matter power spectrum is also available as a Python package called Unequal-time. And this is what I'm gonna focus now. I'm gonna tell you about the unequal time correlations. And this is already available on arXiv and also as a Python package, Unequal-time. Right, so, okay. I mentioned at the beginning that if you want to explore the universe, what you have to do is to compute two-point functions. And to compute the two-point functions, we rely in a universe which is homogeneous and isotropic. And if you do so, you can compute, for example, the equal time power spectrum at the same time slice. And this is basically, this is the definition that you all know, is basically the correlation between two different density fields at different scales, but the same redshift Z. And then if you want to go or compute the unequal time power spectrum, which is the correlation between fields at different time slices, you can do it straightforward. instead of having this correlation between fields at different scales and the same redshift, just basically use two different redshifts and you have the unequal time matter power spectrum. And to give you an idea of how these things work, well, the equations are really overwhelming, but in linear theory, this is really simple. In linear theory, the equal time matter power spectrum is what you all know, right? So it's just the squared of the growth function times the power spectrum at some redshift of reference. But then the unequal time counterpart is also simple in linear theory. It's just the product of the growth functions at the two different redshift times the linear power spectrum, right? And as you can imagine, if you set the two different redshift at the same to be the same, you retrieve the equal time power spectrum. But as I mentioned, I was interested in this because I wanted to deal with nonlinear physics. And for that, you need to go to use higher order corrections in perturbation theory. For example, I use one loop theory. In one loop theory, you have the linear contribution, P11, and then you have the one loop contributions, P22 and P13. I did this in standard perturbation theory, but standard perturbation theory it is not able to deal very well with nonlinear physics, and effective field theory is the perfect framework for that. And for those of you who are not very familiar with effective field theory, I'm going to make a parenthesis here, and I'm going to tell you a very short story. I always like to explain EFT using a hot chocolate cup. So imagine that you have a hot chocolate and that you want to measure the density of your hot chocolate. You know, density is a macroscopic quantity, but your hot chocolate is made of hot chocolate particles that are constantly interacting with each other. There is collisions, there is viscosity, and all this messy microscopic physics is affecting your density measurement. And unfortunately, standard perturbation theory doesn't deal very well with all these small scale physics. But effective field theory, what it does is simply encodes all these messy nonlinear physics into one single free-fitting parameter, which is the counter term. And with this is able to give you a much better prediction on increasingly smaller scales. So basically, EFT is standard perturbation theory minus this correction from nonlinear physics. And so I wanted to test this in the context of an equal time power spectrum, but I'm not very convinced that this works very well. So that's why I came up with the idea of the midpoint approximation. And to show you some results about that, well, what I did here is I had all this grid of theories. I have standard perturbation theory, I have effective field theory, and I can compute the geometric approximation for the unequal time power spectrum, or I can compute the full unequal time information. And in this diagram, if you compare things that are in the same column, you are looking at time effects. But if you compare things that are at the same row, you compare nonlinear effects. In this case, what I'm doing is just focusing on the time effect. So basically, I'm comparing standard perturbation theory, the geometric approximation, versus the unequal time description. And these are the black lines that you can find here. And I'm also comparing EFT geometric with EFT unequal time. And these are the red lines in this plot. Right, so for this plot, I computed things at a mean redshift 0.5, and then I changed the redshift separations. So for example, we have the solid lines correspond to a separation of 0.1, and then increasingly larger for the dotted lines, the redshift separation is 0.2. Basically, the idea here is to see what's the error that you make when you use the geometric approximation instead of the unequal time full information, right? And basically you can see that EFT and standard perturbation theory, basically they perform more or less the same, and you get higher error with higher or increasingly larger redshift separations. But then there is this issue with EFT where at some point it breaks. And now the question is, which one is best? this is not a trivial question. This is really difficult to answer because we don't know what the true power spectrum in the universe is yet. The only thing I could say is that, well, EFT breaks at lower K values than standard perturbation theory, and EFT, in theory, it was a framework to deal with nonlinear physics. So this shouldn't be happening. And how do we compare with the real universe? That's really difficult to say. Maybe we need to work more on simulations, and well, this is some future research line that I would like to do, to perform some simulations that can give you the full unequal time information and going beyond symplectic integration methods. But that's something that could be done in the future. But now, what I did was to came up with a new approximation, the midpoint approximation. And here I'm going to compare these three things. I'm going to compare the unequal time power spectrum, which is the full information, the geometric approximation. Remember, that was only the power spectrum at one redshift and the power spectrum at the other redshift, and the midpoint approximation that approximates the full information to the power spectrum at the mean redshift. This is a very similar plot to the previous one. So the red lines correspond to the geometric approximation for two different redshift separations. And then the dark, the black lines corresponds to the midpoint approximation. What can we say here? Well, we can conclude that these approximations are more accurate when you do small separations. But if we focus on the geometric approximation, which is the red lines, we see that this is a very good approximation on very large scales. This is something that we already knew. For example, Lemos et al., they explained in their paper in 2017. But the error increases on increasingly smaller scales. And then when we use the midpoint approximation, yes, it is not perfect on very large scales, but then there is this feature over here that depends on the mean redshift. And perhaps with this feature, well, you can see that the error is much more flat, and perhaps with the features can give you a much better prediction on small scales or mild nonlinear regime. So for now on, I'm only going to talk about standard perturbation theory. Okay, but what is the impact on weak lensing? Okay, so to give you an idea, I'm going to show you some results, and to see the impact on weak lensing, I need to use the software that I mentioned that we developed, Corfu, and we're going to compare all these four prescriptions. First, we're going to compare with the exact calculation, where we use the full unequal time information, and with help of by this Corfu software, we're able to compute these things exactly. And then you can use the inverse approximation, and then the geometric approximation, which looks like this, separating the power spectrum into redshift, and then the midpoint approximation that looks like this, taking the mean redshift. Right, just I wanted to clarify something here, because in the literature, when I've seen that people use the inverse approximation, they seem to apply also the geometric approximation before the inverse approximation. And I must say that doesn't seem to make any sense, because when you directly apply the inverse approximation, you can see that you lose any information from an equal time power spectrum. So you actually don't need to apply the geometric approximation before the inverse approximation. And that being said, well, I can show you some results here. Well, this is not preliminary, sorry, so this is just the final results. This is for using redshift distribution of galaxies from DES year 1 data, but I also applied this to LSST year 10. And here we're looking at cosmic convergence, galaxy clustering, and galaxy-galaxy lensing. And what we are doing here is the angular power spectrum for every of these approximations, inverse, geometric, and the new midpoint approximation. And we compare that with the unequal time prediction. So the closer to one, the closer to the truth. And well, basically, we can see that for all of them, the main conclusion that you can say is that just forget about limbers. Limbers break when you have large angle separations or small values of L. That's something that we already knew, but this is the first time that we see this plot. And basically, what this is telling you is that forget about limbers, you just use any of the unequal time description that you want, because all of them can give you the same prediction. So all the features and all the differences that I've shown you previously with the plots of the unequal time matter power spectrum and all this approximation seems to get washed out when you compute all these integrals. So basically the midpoint or the geometric approximation, they do a great job. And when I compare this with LSST year 10 data, where they have a narrow redshift bin, they show very similar results. So yeah, so let me summarize this part of the talk. So basically, right, so we have learned that the angular correlation functions are very hard to compute. The limbers is the most widely used approximation, and there is this list of issues regarding the accuracy, the validity of different approximations, and there is this need for the unequal time correlators and also the all angular calculation. And we have seen that unequal time effective field theory doesn't seem to improve the standard perturbation prediction. And we have seen that there is a new approximation to the unequal time matter power spectrum, which is the midpoint approximation. And then we have the numeric paper, which is in preparation, where you can have all the machinery for the all angular scale computations with flexibility to include equal and unequal time correlators. And this is available as a Python package called Corfu. And then the science paper, which is already available on arXiv. Well, I explain all these things about the unequal time matter power spectrum, and you have all the software available in UnequalPy. And here we analyze all of the approximations and all the validity regimes. And we have shown that the midpoint and the geometric approximation seems to best mimic the unequal time features. And what we had to do is to forget about limbers. And this is relevant for galaxy, more relevant for galaxy clustering and galaxy-galaxy lensing. Okay, so now I'm going to tell you about the SkyPy project. This is a project that I'm really proud of, and I hope you enjoy this as much. So here I'm going to tell you about different things. I'm going to tell you about the vision of this project. I'm going to tell you about the structure. I'll tell you who we are, and then I'll explain the package and how we are developing the package and the main two key properties of SkyPy, which are the driver capabilities and the research development. Right, so let me start with the vision. As you all know, typically observational cosmology and extragalactic observations have been limited by data access. And that's why collaborations usually formed around data access, for example, Sloan, or Cosmos, or the Dark Energy Survey. But now this seems to be changing. And with the upcoming data, the limiting step is now access to methods. And we do have a fantastic emerging methods like forward modeling and machine learning. So in this context, SkyPy was born actually a year ago. And SkyPy is built around methods, right? So it's an open source off project, a Python package that aims to be AstroPy affiliated with functionality to make end-to-end simulations of the universe and to enable forward modeling and machine learning methods. SkyPy is not trying to replicate any existing code. So our aim is to reuse another AstroPy affiliated packages and also some other existing high quality codes. And right, so regarding the structure, well, we have a management structure, we have a board that manages memberships and policies, and also we are organized in dynamic teams to minimize a permanent SkyPy structure. So you can imagine that, well, we have a task to complete, and for that we form stand-up teams. And then after that task is complete, the team is down and we celebrate. And this is usually done on short time scales, roughly 3 months, and this is working very well. And also just mentioning that SkyPy expect rewards through citations of the package. And we are having a paper very soon in a JUST journal. And then regarding the code structure, SkyPy is driven by science projects, and this is something I will mention later. But this is done as GitHub organization. So I don't know, you can open issues to request or reform some features, to report bugs, and then either yourself or someone else from SkyPy will pick up the issue, write the code, the unit test, the high standard documentation, and push a pull request. And then this code will go under a code review process by someone of the same team and also by the actively involved infrastructure team. And just to mention that we have semantic versioning or stage releases, and yeah, the most recent one is 0.1, but in 2 weeks we'll have version 1.0 out. So who we are? Okay, SkyPy is a small collaboration, but it's an international collaboration, right? So we have people from Manchester, from Portsmouth, and also people from the US and Taiwan. So here in Manchester, we have Sarah Bridle. She is our chair. We have Richard Rollins. He's one of the main coordinators, and he's the main guy in infrastructure. Then we have Juan Pablo and Nicholas also working on infrastructure, Ian Harrison, Laura working on gravitational waves, and myself. I'm now also working in infrastructure as well. And then in Portsmouth, we have Adam Amara, our main coordinator, and Philip working in galaxies, Ginevra working in the connection between halos and galaxies, and then we have Coleman and our fantastic group of gravitational wave people, Ian Harry, Laura Nuttall, and the two Andrews. And then in the US, in Fermilab, we have Brian Nord. He's fantastic. He's our ombudsman. And then Simon Bira in Stanford University, which is our expert in strong lensing. And in Taiwan, we have Keiichi Umetsu and Su-Tien Tam working on galaxy clustering. Right, so let me now explain the package. If you go to our GitHub page, you can find the full information and the full list of all the features that we are implementing. As I said, SkyPy will have the functionality to make end-to-end simulations of the universe. So for that, you need to go from background to spectral rendering or image rendering. And in between, we have many things. We have implemented the power spectrum. We have different functions for that. We mocked CAM power spectrum class. We also have Eisenstein and Hall, halo feeds, and growth functions. And we also have a list of halos that are going to be heavily developed in the upcoming phase. We have already mass functions. You can do some quenching. You also can do some abundance matching. And galaxies is the one that is mostly developed and is going to be the main focus in the 1.0 release. You can find loads of things already in galaxies. You can find mass, you can find luminosity, ellipticity, size, redshift, spectra. And then we are also implementing gravitational waves, supernovae and clusters. And then the next step will be to implement Milky Way contaminations. You can have something about stars and dust. And the idea is to reproduce the images from different experiments like DES, PAU, HSC, DESI, LSST, and Euclid. And for that, obviously, you need image rendering and spectral rendering. And as I said, you can find all the information on our GitHub page. And how we've been developing this and how we are developing this fantastic package. Well, we are doing this in different phases and also different layers of development. As I said, SkyPy was born a year ago. So last year in January, we had our kickoff meeting. We set out everything that we wanted to do, how we wanted to do it. And then we entered into phase one, where we implemented the intrinsic. We started with the power spectrum, the halos, the galaxies. And then in phase two, we worked on the observables. We developed a halo modules. And then we started in intrinsics for supernovae, gravitational waves, and clusters. And then in the phase three, we've been focused on research and development. And then we've continued with the rest of the modules. And this was version 0.3 that was last October. And now we are in phase 4, where we are focusing mainly in galaxies. So, okay, that being said, let me mention now what's the two main properties of SkyPy. And one of them is its driver capabilities. So this is key. So the SkyPy driver runs or is able to run end-to-end pipelines of different functions with different dependencies, and you can generate outputs that looks like tables or or you can make some plots. You can find already some examples in our documentation. The first one, the first plot, if you go to our GitHub page under the examples directory, you can find different YAML files. These are config files where you can set everything that you want to do. You can set all the functions with all the dependencies, and this is done as a dictionary. And then you can run the config file within our SkyPy driver. And for example, here for the abundance matching, you can plot this very simple abundance matching example from the Veil and Striker paper. That basically is telling you that as you can imagine, basically the brightest galaxies will be sitting in the more massive halos, and that's simply what it's telling you. This is just an example of things that you can do. Or for example, you can reproduce the galaxy populations from the Hubble et al. Model. And this is the second plot over here. And this is an example of the Dirichlet coefficients that you can use to create SEDs. Or for example, if you're interested in gravitational waves, you can already reproduce some compact binary merger rates as this one. So yeah, but for example, you can also reproduce this plot. This is the luminosity function using data from the Alhambra survey. And you can see how well with our config file that is already available in SkyPy, you can basically reproduce this plot very easily and with no effort at all. And also something that I'm very proud of, if you're not interested in all that and you're interested in simulating things, you can do that. This is just an example of how you can use SkyPy. You can use SkyPy as you wish. It's just a tool. So in this case, for example, we have simulated lensed galaxies by combining SkyPy and another software, Lens Astronomy, which is done by Simon Birra. And you can have all these fantastic pictures of lensed galaxies. But as I say, this is just an example for you to understand the kind of things that you can do. This is very flexible. You can use SkyPy as you wish, and you can use, for example, the SkyPy driver with another config files that you may have or whatever. Really flexible, yeah, for you. Very well. And the second main point of SkyPy is the research development. I mentioned that SkyPy is driven by a science project. If you go to our GitHub page, you'll find our public repository, SkyPy, with all the features that I just mentioned. But if you're a member of SkyPy, SkyPy is going to help you develop your own research. And yeah, so for example, it can prioritize the creation of some modules, or for example, it can create some infrastructure that you may need. And by helping you finish your project, and then your software will feed the SkyPy public repository. And in this way, SkyPy is going to be continuously growing. And currently we have fantastic research development going on. We have a Galaxy Forecast by Philippe. We have projected ellipticities by Nicolas Tesore. We also have another project on cluster and weak lensing by Keiichi Umetsu and Su Tien Tam. And for example, Dark Sirens with H1 tracers by Ian Harrison and Laura Waltz, and much more to come. But if you're not a member of SkyPy and you do want to contribute to SkyPy, you can, because SkyPy accepts external contributions. Just go to our GitHub page and check everything. Maybe you can contribute. Okay, so to sum up, as I said, SkyPy is a legacy project and it's an open source, high quality Python package that is driven by science projects and that aims to be AstroPy affiliated. It does not replicate existing high quality code, and it has functionality to make end-to-end simulations of the universe, to enable forward modeling and machine learning methods. And what is next? Well, as I said, in 2 weeks, we're going to release our version 1.0, where you can find all the features of Galaxies as a very complete product that you can already use. And we are also planning on applying for funding because, as I said, SkyPy is not, it is a legacy project. It is not only about science, it is not only about a Python package, it is also about committing to equality, diversity, and inclusions. And we have plans to develop some very interesting projects along these lines. So yeah, now it's your turn. Open your terminal and pip install SkyPy or conda install it. You can also clone our repository and start using it, import SkyPy. Thank you very much. Any question?